think have most people come in? Okay, let's get started. This is the last lecture of the algebraic effects and handlers sessions. So today we're going to look at programming with effects and handlers. So far we looked at theory, and yesterday we contemplated making a programming language, and we just saw the crude beginnings of how you do this. After that, you have to figure out a lot of things. Some of them are related to silly stuff like syntax. You have to satisfy Wadler's law. I hope you all know Wadler's law. Anybody who doesn't know Wadler's law should look it up. Not now. So there are a couple of languages that support algebraic effects and handlers. We're going to look at F, well, because I know it best, because I'm one of its authors. With Mattia Prittner, we created F. It was the first language that had algebraic effects and handlers, and it was our experiment in how to do this, and it's still an experiment. It will always be an experiment. So Mattia keeps ripping things out of F and putting something else in. So you have to pay attention to the version. So we now actually, so there's F3, 4, and 5. There's F1 and 2, but I don't know where those would be. Anyway, we're just going to use F. And another worthwhile language which has algebraic effects and handlers, which is actually a real language, is OCaml, but not the main OCaml. You have to go for the multi-core version of OCaml. That's a separate version of OCaml that's developed in OCaml labs. I think eventually they'll merge, I hope. Anyhow, the multi-core OCaml has algebraic effects and handlers as well. And the syntax of F and multi-core OCaml I think it was actually made compatible by Mattia lately. So it's the same thing. You can run F in your browser. I would show you this if the wireless worked. But if you go to the notes, these are on the GitHub. You click and you'll get F in the browser. And of course, if you're a PhD student in PL, you should install a new language before breakfast every day. So there are ways of installing this. Anyway, so you should be aware that what I'm going to do now is when we use a real language like that, there are several things on top of what we were talking about. You'll see, but these are details. The essence stays the same. What we were doing stays the same. So let's have a look first at some examples just to get a feel for it. So let's look at exceptions. Here's an F program, so I'll take you through this one. Okay, so what you do is we can declare a new operation. So some operations are built in the environment. The external environment provides them. But here we have an expression. Here we are declaring a new operation called abort, and it's called effect. Just so that I don't know why it's called an effect. It used to be called operation. Nowadays it's called effect. Oh yes, because we're compatible with multi-core OCaml. So we declare a new operation abort, and we give it signature. This is the parameter, and this is the arity. So we know it's the parameter and the arity, but of course, when the programmer will see this, they'll say, aha, this is like a function with this input and that output. That works because the programmer is only aware of the generic operation, which then actually does act like that, like an effectful function. So this is a neat trick. So here's an example. It's a function which takes a Boolean, and then it just does some random stuff here. And then when it comes here to this if, depending on the Boolean it got, it will either abort, so it will raise an exception, or it's not going to abort. And so now let's look at several possibilities. So first of all, let me just get rid of the handler. If I get rid of the handler, then I will load it in, and now I can run it. And so if I give it true, if I give it false, nothing should happen, right? So I give it false, and then it just computes. But if I give it true, it's going to run the operation, abort, and the top level will say, well, we have an uncaught effect because there is no handler that caught it. And this is what happens with exceptions anyway. And this is what is now going to happen with any operation that is not handled away. If it's an operation that the program knows about, then it'll do the global effect, the real effect. But otherwise, it'll just say an uncaught operation. So let's put that in. And now here's the handler. And so this is the return case. So in F, you don't have to write a return or anything. So you just say, well, if you get a value, just increase it by 20. So when I don't run if the exception doesn't happen, I should get 7 plus 8 is 15 plus 20 is 35. But if you get the exception, and here's how you, here is how we explain in a handler what happens. So if abort happens, and so you see here, if this happens, it's abort, and K is the continuation, okay? K is the continuation, then we just say 42. So it's like an exception handler. This one is still 35, but now this one, with the exception installed, is 42. This may look a bit weird up here, yes, because you would expect that here I just say that. Okay? Just, this is how you run. The perform is a keyword that actually activates an operation. Why is Merlin turned on? Go away. Thank you. So with this, now it looks like it's going to work, but can you tell me what's going to go wrong? What is the type of this branch of if then else? What is its type? It's int. What is the type of this branch? What does abort return? It returns empty. So one branch has type empty and the other one has type int. That's a type error. Which is exactly what it's saying. It's saying this expression has type empty, but it should be int. So this mysterious thing here is a match statement on this value here, right? It's saying match on the empty value. Perform abort. This is going to return a value of type empty. Yes, whatever that might be. It returns a value of type empty. We're going to match on it and consider all possible cases of what we could have gotten. And the all possible cases are written here between the letter H and the closing parenthesis. Yeah? That's why we need it. Okay, exceptions? Any question? Yes?
And the matching expression is between the H and match and the other form?
Say again? The matching?
The matching expression, which is between the H and match and the being performed. So I mean, you literally can match on empty by writing nothing?
Here, no, here you have to write something of type empty.
Not there, I'm having to write match performed.
Let me change the syntax and then you will ask the question again. What is your question?
There is result now.
Yeah, so I was just inlining that. Actually, what happens is, this is what will really happen when I run the thing I had, because what F does is it will hoist out computations. You see, because when we had our syntax of the language, we had to be very careful about values and computations. So officially in the language, you have to be careful and you have to distinguish values and computations. But that is certainly not something that I want to impose on programmers. Programmers will be very unhappy if they have to think about whether something is a value or a computation. So instead, what we do is we allow the programmer to mix things up whichever way they want. And then there is, in the parsing phase, there is a desugaring phase which separates them and inserts these lets whenever they're needed. Okay? So this is what will happen when I write that. Yeah? Okay? That is like a little thing that you need to do when you're programming, when you're designing a programming language for humans. You have to pay attention to humans. It's annoying as hell. Okay, let's look at state. And let's remember to, oh, so now for some reason Merlin didn't get activated. Okay. So I'm just going to transcribe state, and then I'm going to give you a standard state handler, which then I will improve with another gadget that we put in F. So first of all, get, oh, let's do this. This is a trick I don't want to use here. It's a shortcut that I want to avoid, like that. Okay, so what is get? Get, F used to have polymorphic operations, which then for some reason were removed due to some experiments. And so now we have only non-polymorphic computations. But using in Multicore OCaml, I think you can do whatever you like, and probably you can arrange things to be more polymorphic. So anyhow, here we have let's have unit for our state. So the state is going to hold an int. The state is going to hold an integer, and there are two operations, get and set, which we have seen. And so they're transcribed here. What does a handler look like? So let's understand this handler. So this is the handler, which, do you remember when we were doing state? I wrote at some point that the free state V is isomorphic to S cross V. So this is more or less what we're going to do. The handler is going to, okay, so maybe I have to explain this carefully. So state has these two operations and 4 equations. But the equations are gone. The programming language, when you work with effects and handlers, there are no equations anywhere. Now, how bad is that? It just means that certain things which should be considered equal are not equal. So the way that you understand this is that what we're writing down is more like source code. It's not yet the actual computation. So there are no equations here, and we have to somehow, if we could somehow magically tell the operating system what the equations for get and set are, maybe then magically the programming language could do something about it. But instead what we're going to do is we're going to say, well, we just have 2 operations, and now we're going to explain how you handle them. So I'm not going to use this. What really happens is when I have the get and the set, I have this. I just always have computation trees. And what my handler is doing is it's going to map such trees to this type. So it is going to map computations to functions. So let's see how this works. This is actually the same sort of thing that you do as you do in Haskell when you have the state monad. It's the same thing. You should recognize it. So if I have a value, that should be a function which takes the current state. So I'm going to thread current state through the computation. So a pure computation takes the current state and just returns the value. Okay? Now, how do I get? Suppose somebody wants to get. Then I turn this into a computation which will receive the current state. It will pass the current state to the computation. As a result, you see here, I run the continuation. I say, hey, the current state is S. And the result of this is going to be handled by the handler recursively. Therefore, it's going to be a function which expects state. And so I pass it this state. You really have to do this in the privacy of your mind. Understand this example, what it's doing. So how do we set? If we want to set the state to S prime, to the new state, so this is supposed to be the new state, what do we do? Well, we turn this into a function which returns, which will give us current state, but we ignore current state because we don't need it anymore. And then we tell the continuation, hey, the result is unit, which it should be for set. And then this will be handled into a function which expects state, which we set to S prime. Yeah? So how would we use this? We could use it like this. Here's a little computation which will get the state, store it in X, then it will set the state to 2 times X, and then it will get the state and add 10 to it, and that will be the result. So when I do this, the result of this is going to be, let me show you what it is. So let's understand what F just did. It told me that state prime is a handler. This is the double arrow for the handler. And it's not showing me the effect information. You know, we had the effect information, the dirt. It's not showing the dirt. It's not doing anything with the dirt. But it's showing me nonetheless what the return values are. So it's saying, if you have some computation that returns A's, I will turn that into a computation that returns functions. And these are the functions that expect initial state. And so then the example 1 now, because I have this unit here, and then I do this F, well, what happened? Well, it takes the unit, and it returns a function which expects int, and it will give me an int. Because this computation here, this is a computation which was turned into a function by this handler. So therefore, to actually run the state, I have to run it on the initial state, like that. And then I will actually get example 1. Now we'll go to unit to int. So if I load this into, I can say example 1, I actually see what happens, and it's 70, and I hope that's right. Any questions about this? Okay, so now here's a little bit of syntactic sugar. This is annoying that I have to run like this, and I get a function, and then I have to apply it, and it just doesn't look nice. And then you say, well, maybe we could do it like this. But this isn't any better, because like, who is going to read this? Yeah, let's not do it like this, okay? So what we put in is a slightly better handler. This is a common idiom that you handle your computation and you turn it into something, like a function. And then you always want to do something with it. Like when it's a function, you want to run it in the initial state. Or maybe, you know, you don't turn it into a function, you turn it into, I don't know, a tree. And then afterwards, you want to do something with the tree. So we made it possible for a handler to have a clause that says, what do you do after you're done? Like when you get the gadget out, how do you transform it? And this is the finally clause, which is not really adding anything to the theory of algebraic effects and handlers. It's just a convenience that says, and by the way, after you've handled this whole thing and you're going to get something, namely some f, here's what you do with it. So now I have a function state which takes the initial value and it returns a handler. And this handler works by handling as before, except that then finally, after it's done, it also runs the state on the initial state. So here's the same thing again, but now you say, I'm going to handle with the state handler with the initial state 30. And then it'll just run it, and now it looks better. And this one, surprise, surprise, is also 70. Any questions? Okay, should we go on? Because we have more, yeah, there's a question there.
It seems a bit unfortunate that you could have unhandled state in your program.
It seems unfortunate that you could have unhandled state. It seems unfortunate that you could have unhandled operations of any kind, right? I mean, I can generalize your complaints to anything could in principle go unhandled. Is that your point?
I mean, that might be more natural for exceptions because there are so many possible ones that could be raised.
Yes. Right, so you are morally happy with, you think that other operations are repugnant when unhandled.
Okay.
Right?
Sure.
It's a fair position. I sympathize with you. So, from a PL design point of view, what would you do? So let's first discuss what you couldn't do. You could not have the compiler predict whether everything will get handled, because that is not correctly all the time, because that is an undecidable question. So let's not do that. We need to do an approximation to that. But I think there are two things to think about. First of all, what can we do, and do we want to do it? Yes? So what can we do is, well, we could use the effect system to analyze which effects may happen, and then if the programmer says this computation here is not supposed to have any effects, then we're going to complain if they say so. All right? But I would be very careful with saying that it is an error for an unhandled operation to appear. I think you need to leave this, it has to be the programmer who decides whether that really is an error. Right?
Can you create I mean, I see how this makes sense for like if you want something that are like global variables, which you might then eliminate at a higher level. But is there a way to create a scoped version of state?
A scoped version of?
State.
You mean what? Like making sure it's not going to escape?
Yes.
Yes, so this is a general question. Can we make sure that operations don't escape? Now, it's not easy to do that, because in principle what you can do is, inside some piece of code, suppose you have like something like locally scoped operations. So you have a locally scoped operation, and inside of this piece of code, you stick your operation inside a lambda, inside some tree, you bury it somewhere, okay, inside some closure. And then you let this be your result. And so now the poor compiler has to figure out that you hid this thing in there. So it seems quite difficult to make sure that it's not going to happen. But nonetheless, an effect system can do this sort of thing. I think we don't have sufficient experience to know, frankly, I think we don't have sufficient experience to know whether this will work well in practice. There's one thing I know. I don't want to use, one of the reasons I don't like Haskell is because I can't put prints anywhere. So, you have to think about that. So it may be the case that we want a system where some operations may go unhandled because we consider those to be innocuous, whereas maybe other operations we really want to restrict them to a scope and they must not escape. I don't know what good practice is because it's too early to tell. That's why you're PhD students. You can do all this. Hey, there was another question. No? It's gone. Okay. Now, let's look at interesting examples. So when you have a handler, in general, the handler has access to the continuation. It gets the kappa. And so it can do whatever it likes with this kappa. And a simple, like if you think about it, what could it do? Well, first of all, it could ignore the continuation. Like the exception handler here, it gets the exception, but it ignores it. It doesn't use it at all. So that would be, when that happens, let's say that that's an exception-like handler. Actually, it is an exception handler. So it's not going to invoke the continuation at all. Another possibility is that it is going to invoke the continuation exactly once. Let's look at the state handler. Here, get gets the continuation, and it restarts it exactly once. Inside a function, but nonetheless, it's a linear use of kappa. And here as well. So this is a single shot handler. Many effects are like this: read, print, get, put. So the ones that are look a bit like some sort of a callback or something like that, because they appear to the programmer like, I'm running the operation jumps out, does something with the operating system, external world, comes back, we continue working as usual, we just get the result. So those would be the single shot continuations. And then you can have multi-shot continuations where there's no reason why you wouldn't run the continuation several times. You can in a piece of code. You get the K, you just run it twice. Why not? So you can also do that. And those would be multi-shot handlers. And we're now going to look at one of them. And they're by far the most interesting and strange ones because they do really things to your flow control. Because those are the ones that are going to be confusing because things will happen twice, 3 times, or maybe you don't know how many times they will happen. Mind you, of course, because the handler can do anything it likes, it could do none of these things. Maybe it's doing something where you can't even reasonably count how many times it invoked a continuation. And we're going to see an example of that as well. Okay, so let's look at one that is multi-shot. Oh, one other thing. If you think in terms of compilation and how you might implement these things, a continuation is really like a piece of stack. It's whatever is waiting for you to do on the stack. So it's like a stack frame. And now if you know ahead of time that it's a single shot continuation, then that's quite useful because you know that once you run it, you don't have to keep a copy of it around because it will never be run again, right? So it pays to know whether it's a single shot or a multi-shot. So it looks like you want some sort of linearity analysis there. And in fact, the Multicore OCaml is explicit about this. Because they care about efficiency, they implemented single shot continuations so that they work fast. Because most uses of handlers seem to be single shot. So they optimized for that case. So if you want a multi-shot continuation, you have to explicitly copy it in Multicore OCaml for further uses. Furthermore, if you have an exception-like handler, in Multicore OCaml, they want you to dispose of the continuation explicitly so they can get rid of it, so that they can garbage collect it, so that they know that it's not getting used at some future time. So those are now intentional considerations that we did not see in the theory. They have to do with how things get executed. They're also showing you something else. These are low-level details that you don't want to use every day. So maybe the good practice will show that the use of handlers needs to be, maybe with, you have to do it with taste. You shouldn't just use handlers for everything. Like, I want to add numbers, let's use handlers. Maybe not. Maybe handlers are heavy-duty control mechanism. So it's likely that certain patterns of usage will emerge, have already emerged and are emerging, like asynchronous threads, awaits, semaphores, I don't know, coroutines. And maybe the common programmer will not keep writing new handlers every day. It's maybe more for a library writer. I don't know. We're just exploring possibilities. We are the researchers. We can do whatever we please, right?
Can you use effects in the handlers?
Yes, you can use effects in the handlers because on this side, and we will do so, on this side of the handler, right, this is a computation. So it can do whatever it likes. And we'll see examples like that. We'll even have a recursive handler where the handler is defined recursively because it uses itself in the handling. Okay, let's look at one of these multi-shot continuations. So ambivalent choice. Here's ambivalent choice. I will describe the computational effect to you, which looks like, it's magic. Okay, here's how it works. So first of all, it has an exception called fail. You use fail. Fail means we failed. The computation did not succeed for whatever reason. And there is another operation called choose. And you present choose. Choose is an operation, and you give it a list of choices. And then it's supposed to choose one of the elements in such a way that in the future, fail will not happen. Yes? It needs to predict future and say, choose one such that fail does not happen. Now, if I had such an operation, could I do anything cool with it? Of course I could, right? I could write nice programs with it. So rather than worrying whether this is possible, let us first write a program that works like this. So maybe the queen's problem. Okay, so let's say, so we're going to have a select, and now I'm just going to choose integers. I just need to choose integers. And so do you know the queen's problem? You are an n by n chessboard, and you're supposed to place n queens together. And let's write a program that does that using magical choice. Because if it's magical choice, it should work really well, right? I just like place the next, I have some queens, and I say, guess where the next queen is supposed to be, and then it will guess, and that's where I'll put it. So here is just an auxiliary function which determines whether locations x, y, and x prime, y prime attack each other. This is really good to give to students. This is one of those problems you give to students, and they create 20 lines of code with lots of ifs. And then you show them this, they go like, oh, why am I at the university? So, okay, now, and here's another auxiliary function, and what this one does is, suppose we already placed, here's a list of queens, so it's just a list of coordinates that are already taken, and now we would like to place we'd like to place something in column X, so we need all the Y's that are available. So what we do is we just filter all the possible, apparently this is doing only queens up to 8, which is rather embarrassing, because this n here doesn't actually do anything. There we go. Okay, so we're just going to do queens. No n, 8 queens, okay. We can do 8 queens. So this one says filter the list 1 to 8 and take those Y's which are not attacked. Yes? So let's see if this works. Yeah, well, now I need to fix the rest of the program. There we go. So I could say, just to see whether this works, available. What's available in the first column if there are no queens? What's available in the first column if there is a queen at 2, 3? Yes, it gives me the available Y's. Okay, and now I'm going to solve queens by magic here. Okay, I just run, it's essentially a for loop. There used to be a for loop in F, and so I used to write this as a for loop, and it looked even better. But now I have to simulate the for loop with a recursive function. Okay, suppose suppose we already placed these queens, and now we're placing queen into column X. First of all, if X is 9, we're done, we just return the queens. Otherwise, we magically select the correct Y from the available queens, and we move to the next column, and we just say, well, now we also have a queen at XY. And then we run with the initial state, which is 1, an empty list. So it would be really nice if we can write programs like this. And so why not? Let's write them like this. There is just the minor detail of implementing select. How are we going to have, oh, this is choose select, okay, select. How are we going to do this? Well, actually, it's a form of search, because when presented with a list of choices and you need to pick the right one, realistically speaking, you just have to try them, right? You cannot guess it. So you have to try them, and then some of them will fail and some of them will not fail. So this is a form of search. But the way the search is happening is that there isn't an explicit search structure present in the code. See, this code here, for solving the problem, doesn't have, it's not imposing a search strategy. It's just telling you, here's what I want to do. And now the search strategy is the handler. The handler will determine the search strategy. And so we can have different kinds of handlers for different kinds of search strategies. By handling the same piece of code with these different handlers, we get different searches. So we are separating the search strategy from what actually needs to be done. So here is depth first search, and one of the problems is to implement the breadth first search. For that you need a queue. So you can also get, there's going to be an example with a stateful queue, so you could reuse that one. So how do we implement magical select? It's not magical, of course. So if we got a value, we got a value, so then we're done. We don't, and in fact, in F, you don't have to write this. It's assumed. Yeah? You don't have to explain that if you have a value, then you have a value. Okay, so what if you're supposed to select from the list? Then, well, you just try them all. So here's a little auxiliary function, triumph, which will try them all. So how does it work? If it ran out, if you tell it to select from the empty list, that means that it cannot proceed. There is nothing to select. This is when fail will happen. It has to fail because it cannot succeed. It cannot select anything. So it fails with the usual proviso that this is of type empty, and so therefore we have to do the empty match here. Of course, you wouldn't write this all the time in your code. You would give yourself an auxiliary function for failing. So if you look at how F does this, it doesn't actually do this. Okay, so what if I have an available X to try? Well, what do? You see now here, I am further handling inside the handler. So I give X to the continuation. So I say, hey, K, here's your X. And so K will run with it, and two things may happen. Because this K will further get handled with my handler. So two things will happen. Either it will produce a value, in which case, that's okay. It found a value. Or it's going to fail. But if it fails, then I will handle that and try the rest. And then I'm done. And so now I have depth first search. Questions? So then we can solve the 8 queens problem. And here they are. Okay? Can we go on? Yes?
What happens if there's no solution for all choices?
If there is no solution, so suppose here I made a mistake and I wrote 19. Okay? So then probably something is going to go wrong. Well, what happened was that it ran out. Eventually, it got to the point where where there were here the available. Nothing was available anymore. When it asked what is available in the 9th column among the first 8 rows, it got the empty list, and so then it was forced to fail. But as we heard before, failing like this because it's an exception is morally acceptable. Yes, okay. Okay? Let's have a look at one. Yes?
What if you want to get the list of all the solutions?
Okay, so what if you wanted to get a list of all solutions? Now, let's do this top down. First of all, do you imagine that in principle there is going to be a handler that does that?
Yes.
Yes? So what would this handler do? Yes, but so how would you do that? So at this point here, okay, so here, as soon as we got one, we were happy. Yes? So at this point, we need to do something else. We need to say, we run K of X, and then there will be 2 possibilities. One is that it fails, in which case, when it fails, then we do something else. Yes? Then we possibility. But if it succeeds, we're not done. If it succeeds, we need to proceed anyway. Yes? Okay? So, you know what the other thing is that you should do to your students when you're a professor? It's very, very risky. But write programs in front of them. Let's have another handler, DFS all, which finds them all, okay? So, we are going to find the list of solutions. And just because I'm afraid of this, let me change all these, range. Do I have range? Let me do n equals 6. I'm just going to go with 6. I'm afraid there will be too many. Just 40? Kind of, okay. Okay, so let's just go with all of them. Okay, so how would we change? We need to start collecting the solutions. But also the first thing we need to do is this. When we find a solution, we cannot just keep it like this. We have to say we found one solution that we're putting in a list. Yeah, we need to do that. Okay, and then here we say, okay, this handler here, there will be two cases. If it finds a solution, what do we do? Well, we're going to take this solution and we're going to attach to it all the other solutions that we will find. Yes? No, if, let's see. Yes, this one will already find many solutions, so like this. Yes? So this will be it gets recursively handled. It gives me a list of solutions. So this is going to be a list of solutions found with k of x. And then that's it. Aha. Yes. So we can do something better here. We don't have to fail here, you see. Instead of failing, if there's nothing to choose from, we say, well, there weren't any solutions. Okay? And then if somebody fails, that just means that in that branch there was nothing, and we just do this. Right? This one doesn't change now. We could actually get rid of fail at this point. Yeah. But let's keep it. Now comes the fun part where the professor tries to debug his own program. And then it's more than 40. Maybe, who knows? Okay, but there they are. We don't actually, I'm pretty sure nobody actually checked whether these are correct. Right? Yes, so you can do lots and lots of things like this. Okay? Okay, should we look at another one? Okay, let's do cooperative, let's do threads. Threads, I think, were the motivation for putting effects into multicore OCaml. In multicore OCaml, because they're this multicore, you have these different threads running at the same time. And whenever you have threads running at the same time, you face the question on how do I schedule them? What do I do with them? How do I schedule them? And this is a difficult question because it doesn't have a single answer. There is not one single scheduling strategy that will make everybody happy, which is why operating systems have complicated schedulers, and you can set priorities, and it's all very you can have a PhD in that, I'm sure. Right? Also, the same question is faced by the designers of a multi-threaded programming language, because the programming language itself may also want to, the top level needs to schedule things, and maybe it's not just going to hand it over to the operating system. Maybe it will, who knows? Depends on the operating system. Anyhow, it turns out that handlers are a good way for expressing scheduling strategies. And that was one of the reasons that they put them in the multicore OCaml, and they were then quite happy with them. So let's look at how this is done. The point is this, of course, it's written here. With operations and handlers, we have access to continuations. But continuations are like suspended processes, which are like threads. So what the handler can do, instead of running the continuation when it gets it, it could store it in some place and run some other continuation. And that's a scheduler. So let's implement it. So we're going to have we're going to have two effects. The effects are yield, which is because we're doing cooperative multithreading, because the architecture of F is not intrinsically parallel, so I can't really run them in parallel, so I'll have to simulate that. So cooperative multithreading means that one thread runs at a time, and then because it's nice to other threads, and they're all friends, every once in a while the other thread, this running thread says, yeah, I yield, somebody else may run at this point. So that's the yield operation. And I'm still trying to, okay, it's like this. You just say, I yield, and then after a while you will be restarted, but you don't know when. And the other one is spawn. I was told that this is spawn. You know the difference between spawning a process and forking a process? Apparently there is a difference. The difference is who goes first. You see, when you do this in parallel, it doesn't matter, but when it's cooperative multithreading, if one thread spawns the other one, or forks itself, so the question is who goes first, the original thread or the one that got spawned? And you will tell me by looking at the code who goes first, okay? Because somewhere in the handler it will be visible. So how do you spawn a thread? Well, you give a function from unit to unit, which then gets executed. The thread is a function from unit to unit, and you execute it by applying it to unit. We will also, just for the fun of it, so that we can combine handlers, so that we can combine effects, we're going to implement a round-robin scheduler, which means that there's going to be a queue, and we put our threads into the queue. So whenever a thread yields, it goes to the end of the queue, and the guy who is in the front of the queue gets activated. So we need a queue. Let's do a stateful queue using effects. So there is going to be a DQ and an NQ, and maybe it would be better if I did type thread is unit to unit, thread, thread, thread. The beauty of defining types. If only programming languages that people use, that would be so nice. Anyhow, let's see. So you can dequeue, in which case you will get the next thread to run, but it's an option because the queue could be empty. And if it's empty, then we're done. There are no threads to be run, but it's finished, we're done. Or we can encode a thread. Okay, here's the queue handler. So how do I dequeue? So this is now a state handler. Queue is state thing, so it's going to be, this is now a state-like handler, but it's handling an entire queue. So how do I dequeue? Well, I look at my queue, that's my state. I look at my queue, and then I don't know, why is it like this? It could be just a function. Okay, so I look at my queue and I say, if it's empty, then I cannot dequeue. So I tell the continuation, hey, the continuation, there is nothing to dequeue, and the next state is that this is my queue, it's still empty. If there is a first element of the queue and the tail, then I give k the head, I say, here's the thing that I dequeued, and the state is the rest of the queue. How do I enqueue? Well, I enqueue by taking the current queue, I tell the continuation that the result is unit, and then I place the thing that is supposed to be enqueued, which is a thread, at the end of the queue. And this is the same as the state handler. When you're done, you throw away the queue, and finally you have to run it on the initial state. Okay, and now how about the scheduler for the round robin? Okay, so here's the round robin thread scheduler. Notice that this is going to be a recursively defined handler. So we're going to define a handler which uses itself while it's handling things. And this is seen here. It's a recursive handler H. But here is, first of all, this is not needed. There we go. I hope. It is more dangerous as a professor in front of students to make small irrelevant changes to your source code than it is to write new source code. Because when you write new source code, everybody knows you're going to make mistakes. But when you make small irrelevant changes, everybody expects that they're small and irrelevant. Okay, apparently we're dequeuing twice or something here. But this looks like the same thing, so I will make this small irrelevant change here. There we go. Okay, so just because I'm dequeuing twice, let me see, how do I dequeue a thread? This should really be called, this should be called dequeue thread. There we go. So I perform the operation dequeue, and if I get nothing, I'm done. If I get a thread, I activate it by applying it to unit. And here's my recursive handler H. So how do I handle yield? A process says, I yield, please put me in the queue. Well, it's very easy. I put the process in the queue, and then I dequeue. There's nothing to be done. Yeah, that's it. Okay? How do I spawn a new thread, T? And now you will tell me who goes first. The child or the parent? The child goes here. I am enqueuing kappa. So I'm enqueuing the rest of the process that is doing the spawn. I put that one on hold, and then I run T. But now here comes an important thing. This T is going to yield as well. And when it yields, you see, my handler will make sure that the continuation is handled. This whole thing is not handled unless I explicitly do so. It's not handled again by the same handler. It's handled by the outside handlers. K is handled by this handler. So I want this T also to be handled in the same way using the same queue. Therefore, I need to wrap it again with the handler, and that's where recursion comes in. This H has to be recursive. Continue working on the new thread. So at this point, you should have all sorts of worries. For instance, aren't we going to, like every time we spawn, we're going to envelop whatever's going on with another handler? So there will be lots of nested handlers and stuff. That sounds worrisome. Yeah? But really, this is a general feature. When you simulate effects using something that is not using effects, you will probably pay a price. Often you will pay a price. There is also the other side of the coin, which is how to write compilers that optimize this stuff. And this is also a current area of research. And people have had some very good successes with optimizing away most uses of handlers, because you want to optimize them away so that you don't then just spend your time handling. You want to get to the operations as fast as you can. And what happens if we get a value, which means that the main computation has finished? Well, if the main computation that we're handling has finished, there may still be some other threads running. And so you need to dequeue that. Okay? How are we putting this together? Because we have two handlers. We have one for queues and we have one for threads. Well, what you do is you just nest them. And now you should worry about how you nest them. What if I nest them the other way around? Will that matter? Maybe it will, maybe it won't. This is one of the maybe weaker points of handlers. Once you start combining handlers, you can get counterintuitive results, especially when you combine stateful handlers with multi-shot handlers. That is a recipe for confusion, and I invite you to investigate it. Okay, so here's a silly one. Let's see if we can understand what this does. Okay, so this thing is going to spawn a new thing. And so you see there are two spawns. We're going to spawn one thread, which is here, and then we're going to spawn another thread, which is here. And this is just a function here. This is silly. Let's have an auxiliary function. Print list, iter. So we iterate on the given list. We take a list and we iterate on it, and what we do is we perform print is built into F, so this one is already built in. This will be the top level print. So we print and yield. So each of these processes here, and so this is going to be print list. We're going to print this list. And then we're going to print this list. Okay, this is a better program. So spawn the following. Print this list, and each time you print, you yield. And then do this again. What do you expect to see on the screen? If this works correctly, in what order will things get printed? One from each, right? They should get interleaved because the round robin should interleave them. They got interleaved. Yes? But it doesn't have to be 2 threads. It can be any number of threads. So let's do a crazy one. Let's enumerate all fractions. So let's understand what this does. Maybe let's see what is the time. No, let's not understand what this does. Okay, so here, this one is just going to spawn lots of processes, one per denominator. And it will print out fractions in lowest common. Many threads. Each thread is responsible for one denominator. Yes? And here, it will only go up to 10, denominator 10. So here are all the fractions with denominator at most 10 that are in lowest terms. So if I do lots of them, then it will take some time to do it, and then we should be able to see line 47. I made an insignificant change. Okay, so now it was printing them, and this was lots of threads printing. Fractions, okay, here. So maybe, okay. I mean, you can have a look at this. Here is find fractions, and this one, what this one does is, it just goes through the fractions, and it prints it, and then it yields for somebody else to continue. And what this one is doing is just going to spawn lots of threads, one per denominator. Questions? Let's look at the last example. I wanted to do something strange. Okay, something that is slightly more intellectually interesting, I think, because printing stuff, who cares? Okay, so suppose let's do some cool functional programming. So suppose you have this is not game semantics. Well, actually, Dan's not here, so I could leave this in. But he would probably say it's not game semantics. There, okay. So suppose we have a functional. So what does a function mean? A functional is a function which accepts functions as arguments, right? It's a higher order function. So suppose, just to keep things simple, let's have a functional which takes a function from int to bool. So you can think of this as an infinite sequence of bits. Right? It's an infinite sequence of booleans. This is some function f, and if you say f of 10, it will tell you what the 10th boolean is. And suppose now you're calculating a boolean out of this. Okay? How do we imagine, that's why I said game semantics. How do we imagine this happens? So Dan was telling you that when you run h of f, a certain game is played. But you can also think of this game as, there was this business of asking questions and answers. So the way you can imagine is this. What could this h possibly do with f? Well, it's going to evaluate f at certain points. So think of this as asking f questions. So it'll ask f, hey, what is the result if I give you 10? What do you give me as an answer? So it can ask a question. If h can ask a question, it will ask the question, say, x0, x0. That means it will evaluate f of x naught. And then it'll get an answer. And then depending on whether the answer is true or false, it may do one thing or another. So every time it asks a question, it'll branch off depending into whether the answer was true or false. And so for a while it'll be doing this, and then eventually it'll say, I know the answer. And then it'll stop and it'll give the answer. So this means that we should be able to represent H as a kind of a question-answer tree. So you can think of H as a tree where the nodes are questions and the leaves are answers. And so whenever you ask a question, so when you have a node, so if you get to the end of the tree, so you're at the leaf, that means that the leaf is labeled by the answer that you're supposed to say. And so you say, my answer is whatever is in the leaf. The other possibility is that you say, well, I don't know what the answer is. I need to ask f a question. So when you ask a question, that means that you pick some value x naught, and then you evaluate it at f, and then you get true or false. And depending on whether you got true or false, you do one subtree or the other subtree. And you keep climbing up the subtree. So if I get the answer false, I go to the left subtree. If I get the answer true, I go to the right subtree. We're going to see these trees in a moment when they get computed for us. But in principle, there should be a tree like that. That's a tree representation of a functional. And by the way, I'm secretly teaching you Bauerian intuitionism. Okay, let's see. Can we write down this data type? Sure, we can write down the data type. Here's the data type of trees representing such functionals. You can say the functional could either completely ignore its argument and it will say, well, I know the answer, in which case it has the answer. Or it could say, no, I need to ask a question. So I ask the question, I ask this question. And then if the result is false, if the answer is false, when I ask the question to f, if it says false, then I will use this tree for further computation. Otherwise, I'll use that tree. Or maybe it's the other way around. Okay? Now, if I have a tree, can I convert it to the functional? So if I give you a tree T and the f, can you then tell me how to apply? Well, yes, of course. I look at the tree. I look at the tree and I say, if the tree says that the answer is already known, ignore f and I provide the answer. Otherwise, if I'm supposed to ask a question, well, then I ask f of a question. If f says true, then I continue recursively by climbing up the tree, T1, which is the left one, so it's the other way around from what I said. If f of x says false, then I do T2. Okay? Shouldn't be too complicated. Okay, now let's implement the inverse to this function. Can we have the inverse? You should first object that you cannot have the inverse because there are many inverses. For instance, H could ask useless questions, right? So I could have an H which always says 42, but before it says 42, it asks some useless questions and it ignores the answer. Like in each case, it does the same. So there will be many trees representing the same H, the same functional. And this is intentional information. This means we will exactly be able to detect. Once we build the tree, we will look at the tree. We'll be able to detect what H was doing, how it was interrogating F. So we can recover intentional information. We can recover information about the functioning of a piece of code using effects. It turns out, and this is a little bit of denotational, you need a little bit of denotational semantics of functional languages to know that in a purely functional setting, in general, you can't do this. Actually, because I have let's use effects to do it. Martin Escardo has a very nice blog posts and papers on using these ideas to do all sorts of things in a purely functional setting. So let us look at how to do it using using effects. So what could you do? Okay, so what do you do? How would you do this? What's the idea? Where do you get it from? Somehow, what we need to do is we're going to get H, and we have to get the tree out of H. Just about the only thing we can do with H is that we feed it an F. Yeah? We have to feed it an F. So we have to feed it a magical F. This magical F is going to be full of hidden operations that will do things for us. Namely, it will secretly report to us what H is doing. Okay? So we get an H, we're supposed to get the tree out of it. We can have the tree if we only found out what questions H is asking. So we're going to send in a spy that will report what questions are being asked, and that will get us the tree. Something was wrong there. This underscore, how do I make an underscore in Markdown? Nope. Try again. Apparently by doing a double underscore? No, because this is still... Okay, homework problem, fix this. I will do a stupid fix right now. There we go. Now it really doesn't know what to do. Okay. Fix this without renaming the file is the correct problem. Oh well. Okay, so first we have some repetition of the code. Here is the tree data structure. Here is the tree to fund. This is the easy one. And so now let's do the spy thing. Okay? Our spy needs to have a special secretly report operation. And this secretly report operation will be like this. The spy will say, hey, they're asking the question int. What should I answer? Okay? That's what the report is doing. That's what the spy will do. Whenever anything is asked of our spy, the spy reports back to us through this operation, us being the handler. And then we tell the spy, why don't you tell them it's false? Okay? Or why don't you tell them it's true? Okay? That's what we do. Okay, so here's the entire code. Now let's understand this code. Okay. We are supposed to decode, we're supposed to find out through our spy method what H is doing. And what we're going to do is, we're going to say, actually, we think that H is a constant function. So it's just going to be the tree, which is the answer. But we will change our mind as soon as H asks a question. So here is the spy. You see? It's the spy that is not doing anything. We're giving it a special F, and as soon as this F gets an X, it says, what should I say? It's reporting to X. It's reporting to the handler that X is being interrogated about X. What does the handler do? Here's the handler. So the handler says, they want you to answer they want you to answer the question X. Sure, we can arrange for that. And here is the rest of the computation. And so we say, apparently, H asked the question X. Therefore, its tree representation is question X with two subtrees. What are the two subtrees? Let's find out from the spy. We tell the spy, in one case, we run twice. In one case, we tell the spy, tell them it's false. And the thing gets handled again, and the tree gets constructed. And in the other case, we tell the spy, tell them it's true, and the tree gets constructed, and we have another one. Yep. So this should now enable us to reconstruct the trees. Let's have a look. So first of all, example 1, we try an H. This is my H here. Actually, it's probably better if I call this F everywhere. F, 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 F. It's a trivial and insignificant change. So first we try the constant with constant h, which ignores its f, and it always says true. So this one should give us answer true. Should just give us answer true. Answer true. But I could also, let's try a one where it asks questions for no good reason, okay? It says, I want to know f of 42, and then I want to know, well, I can just do it like this. And then I want to know f of 23, then I say true. So now, here you see, it says, what's the question? How do you answer 40? Like, I ask you 42. And then in this branch here, can you still see this? And then in one branch it goes and it says, I ask you 23, and then in both cases it says true. And here again in both cases, see, we're discovering how things happened. Okay, how about this one? Okay, this is actually this one, okay. I should have looked ahead. Ask a silly question, gave the same answer twice. Okay, how about a non-silly one? Here's one. Okay, so we ask f, hey, what is the result of f of 10? And then if it's true, then we do this thing here. And if it's false, we do that thing there. Okay, it's going to be a 3. It's this 3. And just because I can, because I have 7 minutes, let's draw it. So I start by asking 10. And then there's true and there's false. And the first one says, ask 20. And there's true and there's false. And then in case it's true, this one is false. But here we continue and we say 8 and then true and false. 8, true, false. Okay, how about the other branch? The other branch is 30, and then this, and then it's false, true, false, true, and true. Okay, is it clear how this works? So we can reconstruct. Once you have such trees, then you can do lots and lots of things. For instance, if I give you 2 such trees, can you tell me whether they compute the same functional? Is it possible, given 2 such, well, they have to be finite trees, of course. And they will be finite, provided my functional is continuous, but it is because it's computable. Okay? But if they are finite trees representing functionals, you can actually decide whether they calculate the same, whether they're equal. And there says this one is pretty large. I don't know. Do we want to run it? Of course we want to run it. What does this do? Who knows? But it's pretty large. Well, okay. Well, so much for pretty printing. It's not actually helping. It's not that large. Ah, it's large. $4,000 lines. Okay. I think I'm done. Let's look at the problems. Okay. First question, has anybody solved any of the problems at all? That's the sort of question you should never ask your students. Because the people who did, at this moment, they dare not say yes. Right? And all the others dare not say no. Okay, so first of all, you can try other kinds of strategies. Yes. You could even contemplate doing things like programming games this way. When you have you want to encode the rules of a game, or how a game is played. Well, you just say, okay, and then the opponent moves, and then the proponent moves, and you just say it moves, and that's an operation. But you don't have to explain how. That will be done later by the handlers. There is an example that I didn't go through, which is on the online F, which shows you that you can do the following. You can handle random number generators in a different way so that you get the distribution of the results instead of just one sample. But this is a more complicated example. This is a more complicated problem. But that handler just does exhaustive search. That is to say, it always tries both, like it's flipping coins. So every time you ask it to flip a coin, it flips the coin twice for both. It runs the continuation twice, and it calculates the combined distribution of both flips. But this is exponential in the number of coin flips. So it's not going to work well when you flip lots of coins. So maybe so there should be handlers that do this in a statistical way, so that you can have a trade-off between time and how good your estimate of the distribution is. And then the last one is that you should contemplate the recursive cows. And I'm not going to say anything about this, but this is a warning about the fact that effect systems and effects can be weird. Okay, it's an example which it's an example where recursion appears out of thin air. Okay, and you should try to understand it. Okay, I'll stop here. Thank you.